They had 90 days to build something impossible. 2 million tons of supplies needed to cross the English Channel every month, but there were no ports. The German High Command knew this. They'd destroyed Cherbourg's docks, mined Calais to rubble, fortified every harbour from Belgium to Brittany. Field Marshal Rommel stood on the Atlantic Wall and declared Allied invasion logistics militarily impossible without deep-water ports. He was looking at 200 years of naval doctrine. What he didn't see was the fleet being assembled in absolute secrecy. Artificial harbours larger than Dover, designed to be towed across 100 miles of open ocean, anchored in 60 feet of hostile water while under fire. The numbers seemed like fiction. The execution would rewrite everything the world knew about amphibious warfare. June 6, 1944. 156,000 men hit 5 beaches. Within 48 hours, the math became brutal. Each soldier needed 30 pounds of supplies per day. Each tank burned 300 gallons, crossing 50 miles. Each artillery piece fired shells weighing more than a man. The equation was simple and devastating. Without ports, the invasion would starve in 2 weeks. German generals waited for the logistical collapse they knew was coming. They'd studied Gallipoli, Dieppe, every failed amphibious operation in modern history. The Allies had no ports. Therefore, the Allies would fail. The math was certain. But 15 miles offshore, something was moving through the darkness that would make the math irrelevant. Mulberry Harbour, code name for the most audacious engineering gamble in military history. Picture this: 142 concrete caissons, each one 5 stories tall, each weighing 6,000 tons, being towed at 4 knots across the most unpredictable waters in Europe. Behind them, 23 floating pierheads, 10 miles of flexible roadway, 70 obsolete ships ready to be scuttled as breakwaters. The British called it Mulberry A and Mulberry B, 2 complete artificial ports, prefabricated in Scotland, Wales and England, now crossing the Channel in the largest maritime construction convoy ever attempted. Each caisson was a self-contained fortress. Reinforced concrete walls 3 feet thick, compartmentalized to survive torpedo hits, fitted with anti-aircraft guns and living quarters for 60 men. They'd been built in dry docks, then flooded and towed by ocean-going tugs through submarine-infested waters. The German Navy had no idea they existed. Inscreva-se para mais decisões impossíveis como essa, 2 vídeos por dia. June 9th, 3 days after D-Day, the first caissons reached the Normandy coast. Engineers worked in 12-hour shifts under sporadic artillery fire, positioning each massive block with tolerances measured in inches. The design was brilliant in its audacity. Sink the caissons in a precise line, pump out the water. Suddenly you have a breakwater creating calm water where 6-foot swells had been breaking. Behind the caissons, the scuttled block ships. 70 elderly cargo vessels and warships deliberately sunk in a second protective line. Then came the genius. Floating pierheads that rose and fell 22 feet with the tide, connected to shore by flexible roadways that could handle 2,000 tons of traffic per day. The entire system covered 5 square miles of ocean. It was a port where no port should exist. The numbers started flowing immediately. Day 1, 850 tons landed through improvised jetties. Day 3, 5,000 tons through partially completed sections. Day 7, Mulberry B was operational. 11,000 tons per day, pouring across floating roads that flexed with the waves. German intelligence picked up the reports and dismissed them as Allied propaganda. No artificial harbour could handle that volume. Naval engineering professors had said so for 200 years, but on Gold Beach, British engineers were watching trucks drive across the ocean, on roads that undulated like snakes, delivering ammunition that had been loaded in Portsmouth 18 hours earlier. The impossible was happening at industrial scale, but what they didn't know was coming. June 19th, the worst channel storm in 40 years. Winds hit 45 knots. Waves reached 8 feet. Ships that had survived the Atlantic crossing were torn from their anchors and smashed against the beach. The American Mulberry A, positioned off Omaha Beach, began tearing apart. Caissons broke free, pier heads collapsed. Phoenix breakwater units, each weighing 6,000 tons, were tossed like toys. The flexible roadways that had seemed so clever twisted into scrap metal. In 72 hours, everything flipped. The entire American harbor was destroyed. $100 million in 1944 dollars, equivalent to $1. $7 billion today, reduced to twisted metal and shattered concrete. German commanders monitoring the storm assumed both harbors were finished. The Channel had done what the Wehrmacht couldn't, killed the Allied supply line. They prepared for the counter-offensive that would drive the weakened invasion back into the sea. Panzer divisions were repositioned. Artillery batteries calculated ranges to the beaches. Intelligence estimated the Allies had 7 days of supplies remaining. Then everything changed. What the Germans didn't know was that British engineers had built Mulberry B to different specifications. Heavier caissons, more redundant connections, breakwaters positioned at precisely calculated angles based on 40 years of Channel weather data. While the American harbor died, the British one flexed, adapted, survived. Se inscreva para ver como decisões de design salvaram a invasão. 2 vídeos por dia. June 22nd. Storm clears. Mulberry B at Arromanches is still standing. Not just standing, operational within 6 hours. The flow of supplies resumed as if the storm had been an inconvenience rather than a catastrophe. Here's where the numbers became ridiculous. By July, Mulberry B was landing 7,000 tons per day, more than the pre-war port of Dover. By August, 9,000 tons per day, exceeding Cherbourg's peacetime capacity. By September, when Cherbourg's conventional port was finally cleared and operational, Mulberry B had delivered over 500,000 vehicles, 2.5 million men, and 4 million tons of supplies. A temporary harbour built in 90 days and assembled under fire had outperformed permanent ports that took decades to build. Let that sink in. 2 million tons per month, through a harbour that floated. But the numbers alone don't capture what this meant. The psychological impact on German commanders was devastating. They'd based their entire defensive strategy on a mathematical certainty. Invaders need ports. We've destroyed the ports. Therefore, the invasion will fail. When Mulberry proved that equation wrong, it shattered something deeper than tactics. Blumentritt later wrote, "We never imagined such engineering was possible. It made our Atlantic wall calculations obsolete overnight." Field commanders watching supplies pour across the floating roads realized they weren't fighting an army anymore. They were fighting an industrial system that could turn ocean into infrastructure faster than they could destroy it. Every military academy principle about coastal defense and supply lines had just been invalidated by a harbor that shouldn't exist. Let's talk about what made this insane. Each caisson took 3,000 tons of concrete, 300 tons of steel, 6 weeks to build in specialized dry docks. Britain was simultaneously building bombers, tanks, and ships. Yet they diverted enough resources to construct 142 of these ocean-going fortresses. The engineering challenges were absurd. Concrete that could survive saltwater immersion. They invented new chemical treatments mixing volcanic ash and specific ratios of Portland cement. Trial batches were tested in accelerated corrosion chambers. The first 12 prototypes failed, cracked under pressure testing, degraded in saltwater tanks within weeks. Engineers worked backwards from failure. Each crack revealed what didn't work. Each dissolved section showed which chemical bonds broke down first. By prototype 23, they had concrete that could survive 50 years of ocean immersion. They'd accidentally invented what would become the foundation of modern offshore construction. Caissons that could be towed 100 miles without breaking apart. They designed self-sealing compartments that could be pumped out at sea. If one section flooded, 11 others kept it afloat. Flexible roadways that could handle 40-ton tanks on floating platforms, they created articulated steel spans with buoyancy chambers that adjusted for load. None of this technology existed before 1942. It was all designed, tested, and mass-produced in 24 months while fighting a two-front war. The deception component was equally masterful. German reconnaissance aircraft photographed the caisson construction sites. They saw what looked like coastal defense installations, massive concrete blocks being positioned along the Thames estuary. British intelligence fed the narrative. Anti-submarine barriers, floating anti-aircraft platforms, experimental coastal fortifications. The massive concrete blocks being towed into position before D-Day were explained as temporary breakwaters for training exercises. German spies reported back. The British were building defensive structures. Good. It meant they feared invasion. When Mulberry actually appeared off Normandy, German commanders spent 72 hours convinced it was an elaborate decoy, while the real invasion would hit Calais. By the time they understood what Mulberry represented, 50,000 tons of supplies had already crossed its floating roads. Here's the kicker. The scuttled block ships in the breakwater weren't random old hulks. They were carefully selected for size, weight distribution, and scuttling characteristics. The British sank HMS Centurion, a battleship that had been a decoy in the Mediterranean, in exactly 62 feet of water at precisely calculated coordinates. They scuttled HMS Durban, a light cruiser, in 58 feet. HMS Sumatra, a cargo vessel, in 71 feet. Each ship was positioned not just for location, but for how it would settle on the seabed. The angle of sinking, the distribution of mass, the creation of specific water flow patterns. They sank 70 ships in 48 hours with such precision that the resulting breakwater had gaps at specific points to reduce wave pressure while maintaining protection. It was demolition as architecture, turning naval graveyards into functional infrastructure. German naval engineers, examining the wreckage after the war, discovered that some ships were positioned to create deliberate water flow patterns that actually strengthened the harbor's stability. The currents flowed through the gaps, reducing pressure on the caissons. The settled hulls redirected wave energy downward rather than forward. It wasn't just a breakwater, it was a hydraulic system disguised as wreckage. But here's what nobody talks about. The men who made this happen weren't superhuman. They were dock workers from Glasgow, concrete specialists from Wales, tug captains who'd spent careers hauling barges on the Thames. They were given blueprints for structures that had never been built, told to tow them across waters patrolled by U-boats. Assemble them under artillery fire with tolerances that would make a watchmaker nervous. The tug captain who positioned Caisson 47, a 6,000-ton concrete block, had to place it within 18 inches of its mark, in 4-foot swells, with a crosswind, while German batteries on the cliffs above fired ranging shots. He did it on the first attempt. The engineer who designed the flexible roadway joints tested them by driving a loaded truck back and forth across a section floating in Portsmouth Harbour. 247 passes before he was satisfied the welds would hold. On D-Day Pleasant 12, those joints handled 2,400 vehicle crossings without a single failure. These weren't engineering miracles. They were thousands of people executing impossible tasks with zero margin for error, because failure meant 156,000 men dying on beaches with their backs to the sea. The pressure was absolute. The execution was flawless. Curtas esses números estão destruindo sua mente. September 1944. Mulberry B has been operational for 3 months. Conventional ports are now available. Seaborne cleared. Antwerp opening. The artificial harbour should be obsolete. Instead, it's still outperforming permanent facilities. Why? Because the flexible design that seemed like a weakness was actually revolutionary. Pierheads rose and fell with 20-foot tides without pumps or power. Pure mechanical genius using counterweights and hinged connections. A system so elegant it required no external energy. Gravity and buoyancy did all the work. Roads flexed with waves rather than fighting them, reducing stress points that would crack rigid structures. Each articulated section absorbed wave energy independently. The cumulative effect was a roadway that moved like a snake, but never broke. The harbour adapted to conditions that would shut down conventional ports. On days when Cherbourg closed due to rough seas, Mulberry B kept operating because it was designed to move with the ocean rather than resist it. October 7th, 1944. Waves reach 6 feet. Cherbourg suspends operations. Dover cancels all crossings. Mulberry B handles 8,200 tons that day. Above average. The impossible had become routine. German post-war analysis is fascinating. Blumentrit's staff did a detailed study of why their logistics predictions failed. The conclusion was brutal. They'd assumed the Allies would follow conventional doctrine because that's what rational commanders do. The possibility that an enemy would engineer around the port requirement rather than capture existing ports never entered their calculations. It wasn't a failure of intelligence. It was a failure of imagination. They couldn't conceive that someone would build what amounted to 2 major seaports in 2 years and tow them into position as if ports were disposable infrastructure rather than fixed strategic assets. The conceptual leap required was larger than the engineering leap. Rommel's staff had calculated exactly how long it would take to repair Cherbourg. 6 months minimum, more likely 9. They'd destroyed the cranes, mined the approach channels, collapsed the dry docks, sabotaged the rail connections, demolished the fuel storage facilities. Every Kriegsmarine engineer agreed Cherbourg was unusable until spring 1945 at earliest. And they were right. What they missed was that the Allies simply didn't care about Cherbourg. While German demolition teams planted the last charges, British tugs were already towing caissons out of Scottish harbours. The entire defensive strategy was predicated on a premise the enemy had rejected: final numbers to break your brain. Mulberry B operated for 10 months, 5 times its designed lifespan. In that time it handled 2.5 million men, 500,000 vehicles, 4 million tons of supplies. Peak efficiency, 39% more cargo per day than Dover averaged in 1939. Cost per ton delivered, 60% cheaper than conventional ports when you factor in the absence of port repair and mine clearance. Ships unloaded in 90 minutes versus 6-hour average at damaged conventional ports. The artificial harbour wasn't just a backup plan. It was a superior solution that happened to be mobile. That's the real story. They accidentally invented something better than the thing they were trying to replace. The long-term impact rewrote engineering doctrine. After the war, every major amphibious operation studied Mulberry. Korea 1950, US engineers adapted the flexible pier system for Incheon. Vietnam, floating causeway technology traced directly to Mulberry's articulated roadways. The principles, prefabrication, modular design, flexible connections, calculated redundancy, became standard for offshore construction. Modern oil platforms use caisson technology perfected at Arromanches. The North Sea rigs sitting in 300 feet of water are essentially Mulberry caissons, scaled up and hardened for permanent installation. Floating bridge systems in combat zones trace lineage directly to those roadways that undulated across the channel. Hurricane Katrina, 2005. When New Orleans ports were destroyed, emergency floating docks deployed within 72 hours used designs developed from Mulberry components. Tsunami relief operations in Indonesia, 2004. Modular floating piers delivered by cargo plane, direct descendants of June 1944. The harbour that was supposed to last 6 months demonstrated engineering concepts that would dominate marine construction for 80 years. Today, engineering students study Mulberry as the textbook example of adaptive design under impossible constraints. The challenge was, move impossible tonnage without fixed infrastructure. The solution was, make the infrastructure mobile, modular and smarter than permanent installations. Every element served multiple purposes. Caissons were breakwaters and anti-aircraft platforms and crew quarters. Nothing had a single function because weight and space were too precious for inefficiency. It was engineering at its most ruthless. Every ton of material had to justify its existence or it didn't cross the channel. The comparison to modern logistics is staggering. In 1944, Britain moved 2 million tons monthly across 100 miles of hostile ocean using steam tugs, riveted steel, and concrete mixed by hand. In 2025, global supply chains collapse when a single container ship blocks the Suez Canal for 6 days. The infrastructure we think of as sophisticated is actually far more fragile than what Mulberry represented. A system designed to function under direct enemy fire in the worst weather conditions imaginable. Modern ports can't handle 8-foot swells. Mulberry B handled 8-foot swells while being shelled and still beat its delivery quotas. Everything you've seen was designed by people using slide rules and mechanical calculators. No computer simulations, no finite element analysis. No digital modeling. Engineers with pencils and logarithm tables designed structures that would survive conditions they could only estimate. The margin between success and catastrophic failure was the thickness of a concrete calculation and the accuracy of a weather prediction. They got it right on the first attempt under conditions that would give modern engineers panic attacks. But here's what makes this story perfect. The remains of Mulberry B are still visible at Arromanches. 70 caissons still sit where British engineers positioned them in June 1944. They've survived 80 years of storms that destroyed modern breakwaters. Concrete that was supposed to last 6 months has endured 8 decades of Atlantic weather. The French government tried to remove some blocks in the 1950s. The caissons were so well made that demolition cost more than building new structures, so they left them. Today, they're a monument and a museum, but also a functional breakwater still protecting Arromanches harbour. The temporary solution became permanent because it was built better than things meant to last forever. So here's what the German generals missed. They calculated everything correctly. Tonnage requirements, shipping capacity, the logistics crisis from destroyed ports. They were right about all of it. What they missed was the possibility that the Allies would simply ignore the premise of the problem. You need ports to invade? Build your own? You need calm water? Sink 70 ships and create it. You need stable loading docks? Make them float. The solution wasn't to solve the logistics problem. It was to engineer around the entire concept of the problem existing. That's not just clever. That's a different way of thinking about what's possible when resources and consequences force you past conventional limitations. June 1945. War in Europe is over. The final caisson is towed away in November, 5 months after surrender. It had been designed to last 6 months total. It operated for 17 months and was still functional when they took it down. The temporary solution outlasted the war it was built to win. And 80 years later, it's still there, proving that when humans face impossible odds with absolute necessity, we don't just meet the challenge. We build solutions that outlast everything that comes after. Subscribe for more impossible engineering that rewrote the rules. 2 videos daily showing you the decisions that changed everything when everyone said it couldn't be done.